Today in Math 30-1, we're taking the last topic from Chapter 10, Topic 10.3 on composite functions. To compute the square root of 2 times 7 minus 3 on many graphing calculators, the entire expression can be entered in one step. However, on some calculators, the expression must be entered in sequential steps. In this example, the expression 2 times 7 minus 3, and press the equals button, which evaluates the calculation as 11. Then, press the square root of m button, which results in the square root of 11, or 3.3166. The output of the expression 2 times 7 minus 3 is used as the input for the square root operation. Composite functions are functions that are formed from two functions, f of x and g of x, in which the output or result or the answer of the first function is used as the input or the starting point for the other function. For example, if f of x is equal to the square root of x and g of x is equal to the 2x minus 3, then the composition of f of x and g of x is f of g of x, which is the square root of 2x minus 3, as shown in our mapping diagram. It is important to note that the order that we do things in is very important. F of g of x is not going to be the same of g of f of x. They're going to be two separate functions, and they're going to give you two separate solutions. Let's look at example 1. Evaluate a composite function. Here we have three functions. F of x is 4 times x, g of x is x plus 6, h of x is x squared. Determine each value. For a, we want to find f of g of 3. Well, first of all, what we're going to do is plug 3 into g of x. G of 3, which is x plus 6, is going to be 3 plus 6, and that's going to give us 9. Now, f of g of 3 is going to become f of 9. F of 9 is 4x. 4 times 9 is 36. So f of g of 3 is 36. Before we go on to b, we can say, using algebra, f of x plus 6 is going to be 4 times x plus 6, or 4x plus 24, and 4 times 3 plus 24 is 12 plus 24 is 36. So both ways it can be calculated. In b, to find h of negative 2, and then g of h of negative 2. H of x is going to be x squared. H of negative 2 is negative 2 squared, which is, of course, positive 4. And now g of h of negative 2 is g of 4, and that's 4 plus 6, which is going to be 10. Last, find h of 2. So we're going to plug in 2 into h, and we're going to get the answer, and that's going to be 4. And then we're going to plug it in again, and we're going to get 4 squared, which is 16. Or we can do it the algebraic way and go x squared, which is x to the 4th, and 2 to the 4th is also 16. In example 2, composite functions with restrictions. Consider f of x is equal to the root of x minus 1, and g of x is x squared. Now determine f of g of x and g of f of x, and state the domain of f, g, f of x, f of g of x, and g of f of x. Here we go. A. Determine f of g of x. Well, that means that we first of all have to figure out what g of x is. That's x squared. And then plug it into f of x. So we're going to get x squared minus 1. G of f of x is x minus 1, and then we're going to square that, and so then we're just going to get x minus 1. Order does matter, and that's what we're showing you here. F of g of x is definitely not the same as g of f of x. In b, domains. Well, our first function, f at x, is the square root of x minus 1. In this one, x has to be greater than or equal to 1, otherwise it'll be a non-real number. In g of x squared, x can be any real number. F of g of x worked out to be the square root of x squared minus 1. Now, this is a different one because x can be any value greater than positive 1, but it can also be any value less than negative 1. It just cannot be any numbers between negative 1 and positive 1. G of f of x is simply x minus 1, and again, that's going to be any real number. However, g of f of x, which is the domain of f at x, carries forward to g of f of x. So the domain of f at x, which is x is greater than 1, carries into g of f of x. Therefore, in the end, we have to say that g of f of x is only going to be available for x is greater than or equal to 1. That's a restriction carried forward. Here in example 3, we're going to determine the composition of two functions. F at x is simply x plus 1, g of x is x squared. Determine the equation of each composite function, graph it, state its domain and range. Well, f of g of x means f of x squared, which means we plug it into f at x, that's x squared plus 1. That's going to be a parabola. It's going to have a bottom at the point x is 0, y is going to be 1. So therefore, that's what a picture of it's going to look like. The domain is x is any real number, and the range is going to be y is greater than 1 or equal to 1. For b, y is g of f of x. So that means that g of f of x is going to be g of x plus 1 and x plus 1 squared. So when you expand that, it's going to be x squared plus 2x plus 1. That means it's going to have a root at negative 1, and that's what it's going to look like. Now we're going to say the domain is any real number, and the range, y has got to be greater than or equal to 0. F of x. And this means we're going to take f at x, plug it into f of x. So you're going to get x plus 1, and you're going to plug that into x plus 1, and you're going to end up with x plus 1 or x plus 2. That's going to simply be a line that looks like this. And from that line, you can tell that x can be any real number for the domain, and y is going to be any real number for the range. For d, g of x. This time we're going to take x squared and plug it into x squared, and you're going to get x to the 4th. And when you graph x to the 4th, it's simply going to look like this. And again, the domain, x is going to be any real number, as it is for all parabolas, but the range is going to be y has to be greater than or equal to 0, and any real number. Here in example 4, determine the original function from a composition. Well, we're looking at a composition h of x, which is f of g of x. Something is g of x is inside of the function f of x. So when you look at for something inside of x minus 2 squared plus x minus 2 plus 1, I would think of this, first of all, meaning that g of x, the part on the inside, would be the x minus 2. And then on the outside would be what we substituted it into, could be the x squared plus x plus 1. So if you think of where we circled the red and just replace that with an x, that was the original function f at x. We plugged g of x into f at x to come up with x minus 2 squared plus x minus 2 plus 1. In b, let's look at x, the square root of x cubed plus 1. Well, something simple that pops up here is if g of x was the part underneath the root sign, and that is x cubed plus 1. And then f at x could be the part that is underneath the root sign, or just the square root of x. This would mean that h of x would be f of g of x, meaning we would take the x cubed plus 3 and plug it in where the x is right now to get h of x. So in review, here's our key ideas. Two functions, f of x and g of x, can be combined using composition of 2 to produce two new functions, f of g of x and g of f of x. To evaluate a composite function, f of g of x at a specific value, substitute the value into the equation for g of x first, and then substitute the result of that into f at x and evaluate it. Or determine the composite function first and then evaluate for the value of x, algebraically. To determine the equation of a composite function, substitute the second function into the first function as you read it from left to right. To compose f of g of x, substitute the equation of g of x into the equation of f at x. And lastly, the domain of f of g of x is the set of all values of x in the domain of g for which g of x is in the domain of f. Restrictions on the inner function as well as the composite function must be considered. The assignment for this lesson is on page 507, and I'd like you to do questions 1 to 11.